Alright, welcome back again everyone. In this video we're going to start to work on building a bridge between Module 1, which is mostly about the overall philosophy and univariate statistics, and Module 2, which is about regression. We're going to start off with some of the univariate statistics again. This class, being data analytics as opposed to data science, is not so much about all of the cool tricks that you might be able to find in the menus in Excel or in R or in Python or in your favorite statistical software. But this class is a little bit more about the statistics that you can calculate using a data set like what I have here in front of me and how you interpret those. So I'm going to jump in with one of my favorite old data sets, which is Tesla stock. And if you know Tesla stock, well then this is very interesting. I've got some stock prices here from 2021, and as you see on the left I've got the date. I've got opening prices every day. I've got the intraday high, the highest price that a stock sold at on a given day, and I've also got the low. So you can see on this day there was quite a difference between the highest price somebody paid for a share of the stock and the lowest price that somebody paid for a share of the stock. But the closing price in column E is probably what you're most interested in. If you happen to check your portfolio after a long day of work, say it's 5 o'clock and the market is already closed, this is what you're going to see, and this is perhaps going to be your benchmark, because once the market is closed, this is the number that you think the stock price is worth until it opens again on the next day. So this is all very interesting, including the opening price, but closing price seems to be maybe the thing that you're most interested in. Now, opening up any raw data set like this is going to perhaps introduce you to multiple ways of measuring the same thing. And in fact, that's what we see here. The open, the high, the low, and the closing price are all daily measures of what the stock price was on that day. Actually, many different shares were sold on this day. I've got volume over here, which is the number of shares that were sold. And there is a distribution, as with some of these other variables that we're working with, just like there's a distribution across time of the closing prices. Within a day, many shares are sold, and I could, if I had the sale prices for all of those shares, plot the distribution within the day and talk about the intraday average price, the minimum price, the maximum price I have represented here as the high and low, but perhaps there's a mode, perhaps there are some other things that are interesting to look at. So I'll imagine that I've never seen this data set before, and I'll go through and I'll say, open, high, low. The close is kind of interesting, so I'll highlight that. Go to insert. Think about the type of plot that might be most interesting for these. A histogram is going to do a lot of work as far as looking at distributions of numbers. If I want to know the shape of the closing price distribution in general, I can do that. This is perhaps not the way that you would be most interested in representing this data because it's a time series. A line plot might make a lot more sense. But here I see, based on the baskets, and I can format the axis and change the size of these baskets, but based on the baskets I see that there are something like 55 observations between 620, 709. There are something a little bit more, again, oh look, 56 observations between 709.83 and 798.83. These numbers in the 620 to 798 range, let's say, seem to be more frequent, and then it has this bit of a long right tail. Apparently there were some observations up here above 1154, so there were a couple of days where the price was very high. That's a sort of unnatural representation of a time series, so let's try something else. I go back to Insert, and I say, give me a line plot. That seems like a good idea. There it is. Okay, so I can see that, in fact, for many days, I have the counts of the days down here. Wow. So for 90 trading days, roughly, it was in this sort of a regime, whatever this is, a fairly smooth upward slope to it. Then it popped quite a lot. It did some zigzagging and maybe a little bit of a downward trend for a bit. Another large zigzag, if you want to call that popping back up. Some more downward trend, and then a bit of a level off. This is what most stock prices look like. They tend to have this sort of Brownian motion, or there are many different models for motion like this. It's just very characteristic of a stock price over time, that it should follow some sort of irregular pattern, and we'll discuss those a bit more in Module 3. Okay, so fair enough. I've got some data. It has some shape to it. What can I do with it? Start by putting together a couple of simple things. Suppose I'm interested in the distributions within a day, and I ask about the distance between the high price and the low price because I'm interested in some measure of how efficient the market is. If everybody agrees on what the price for a stock should be, then the high price and the low price on a given day should be pretty much the same. There shouldn't be a giant gulf between what somebody is willing to pay at one moment and what somebody is willing to pay at another moment, although that might still be there if the price is moving, if there's a trend within the day. But we'll try something. I've got a column here labeled intraday range. I'll go ahead and throw in some numbers by saying the intraday range being the difference between the maximum and the minimum of a distribution. And I do at least have the maximum and the minimum of that intraday distribution. I can calculate the intraday range. So let's do it. Equals high minus low on a given day. I hit enter, and there it is, $22.51 difference between the high price and the low price on that day. And then I do a quick survey, and I look down through this column, and I see that, yeah, it's usually in the 10 to 20, perhaps $30 range. I want to represent this information a little bit more concretely, shall we say, with some better granularity. So I go back to insert and I say, give me a histogram of these numbers, and then I'll really know what those intraday ranges look like. And sure enough, there seems to be one day that was absolutely bizarre, or perhaps very, very interesting, where the intraday range was something like 160. But I have these baskets that tell me that usually, notice how this distribution is skewed to the right. There's a long right tail, which means that the average of this distribution is probably larger than the median of this distribution. We may see that again. And you may also say that this day is an outlier because this observation had such a large intraday range. But generally speaking, I see these small numbers, which are, again, something like maybe 10, 20, or 30, even a $40 intraday range. On rare occasions, I'm seeing these large numbers like 80, 90, or triple digits within the day, which seems remarkable in some way. So, fair enough. That's one thing I could calculate using data like this, intraday range. Daily return. Okay, so if I want to know how much the stock has changed relative to a previous day, this is interesting because it is a time series and it has a time dimension. This observation here on the 22nd is very related to this observation here on the 21st, because on this day you thought your stock was worth $6.20. The next day you find out it's worth more, a few dollars more. So let's go ahead and calculate. The difference equal to $6.23 minus what it was on the previous day, which would be $6.20.83. Boom, $2.88. I'll go ahead and double click over here to send that all the way down to the bottom. And I see, in fact, that this is not like the intraday range where I have strictly positive numbers. That makes sense. The high is always going to be at least as large as the low. The daily return is, on occasion, negative. Yes, indeed, putting your money in the stock market carries some risk. Once in a while, the stock prices go down. On this day, the closing price was $7.95 lower than it was on the previous day. Well, I'm interested in that as well, so I go ahead and I pop back up here to insert. One of the things about this daily return, in contrast with the intraday range, which is strictly positive, the daily return should be, because the stock price isn't going to go up a lot every day. That would be crazy. It would get very large very quickly if it did. This should be mostly small numbers, sometimes positive, sometimes negative, and it occurs to me that it might even resemble something like the normal distribution that we know and love. So we're going to use the normal distribution a lot when we start talking about testing hypotheses. We're going to start off even sooner with just making a confidence interval for your estimate of a sample average, of a population average, meaning the sample average being used as a stand-in for the population average that you don't know. But we'll come back to that. I want to start off with some real data, these daily returns, sometimes positive, sometimes negative, just like a normal distribution. And we'll go ahead and look at the histogram, and spoiler alert, it is going to have a bit of that same kind of shape. And you can do a lot with the axes, for instance, and go through and say number of bins. Let's try it with instead of 15 bins, let's try it with 20 bins and see if it looks a little bit more like a normal distribution. Interesting. Okay, it seems like that shape is generally there, 25 bins. Or you could make it very ugly and say we only want 8 bins. Interesting. Interesting. Now, financial time series data like this one, daily returns in the stock market, has been studied a lot, as you can imagine, because there's a lot of money in that. And it turns out that this is not usually something like a normal distribution. The tail is a little bit too fat. Actually, we had a pretty good picture of that. Let's go back to say 20. This peak in the center is a bit too tall, and these tails are a bit too long. So instead of looking like this, I should have taller tails over here, more observations way out there, and then a spike in the middle that goes up a little bit higher, narrower shoulders, and then again, more stuff out here, somewhere like 3 or 4 standard deviations above average. These stock returns have excess kurtosis, so we can describe the shape of a distribution in terms of the mean, the median, the mode, the standard deviation, how much it's spread out, skewness, as we saw with the intraday range, which was skewed to the right, and kurtosis, which we see here in terms of having sort of fat tails and a bit of an extra peak in the center relative to a normal distribution. So there are many ways we can parse that information. The skewness and the kurtosis that we see here in the intraday range and these daily returns hopefully are fairly obvious in terms of how they stand out. The mean and the standard deviation are the ones that are really going to do a lot of work for us as far as putting together hypothesis tests and putting together confidence intervals. So we'll focus on that. The standard deviation is just the square root of the variance. So if I refer to the mean and the variance as the ones that do all of the work, I'm talking about the same information as the mean and the standard deviation would be. Okay, fair enough. So I get tired of this chart and I put it away. And then I say, let's see, what else could I do? Okay, so I go up to data analysis, and I remind myself that yes, indeed, Excel had a nice little menu that can do some estimation for me or prepare some of these basic statistics. So I'll go ahead and ask the data and analytics tool pack to give me labels in first row, daily returns here, this entire column. I actually don't know whether it will handle the missing observation in the first column well or not. Different statistical software will behave differently when you feed it a missing value. So notice, of course, I can't calculate the daily return for the first day because it would ask how much this closing price is above what it was the previous day. I don't have the previous day. So I'll go ahead and say, send it to a new worksheet, give me summary statistics, and then I'll click on the OK button just to see if it works with that blank cell sitting right there, looking so intimidating. Excel didn't flinch, so I am happy to report that it worked just fine with one blank observation. And the average return on these days was something like 42 cents. Actually pretty good, although on a stock that costs $600, as a percentage, that's going to be pretty low. The standard error is a very important number. Remember, the standard error is the standard deviation divided by the square root of n. This is not how much the data is spread out. This is something like how far your sample average should be from the population average. So when I make a confidence interval and talk about what the population average would be, I'm talking about what the mean return would be for Tesla stock, not just in this sample, which is from 2021, but in the long run. If I held this stock for a long time and it had the same kind of characteristics across time, I have a small amount of data here that I could use to perhaps, this is very dangerous, you might lose your entire portfolio, but perhaps I could use this data to guess how it will perform in the long run. And if I believe that this sample average is representative of the population average, well, this standard error is about how far the sample average should be from the population average. And when I build a confidence interval, I'm going to use the mean plus or minus some number of standard errors, like 1.96 standard errors, depending on how much of the probability I want to fall within that confidence interval. We're going to try one of these out here in a second. I also see that Interestingly, the median daily return is higher than the average daily return, so it might be a little bit skewed to the right. The mode is something like this. I suppose I believe it. The standard deviation of these, remember, standard error is standard deviation divided by the square root of n. N is down here, 252 observations. So you can do some quick eyeball math and look at the standard deviation and say, does it make sense that this number divided by the square root of 252 would be this number? And I think it does. So I'll pop right over here and say equals standard deviation divided by square root, SQRT, parentheses, 252, and hope for the best. And if it's any different, then there's a degrees of freedom correction. What do I get? Beautiful. 2.23706, that's exactly this number we see up there. Sure enough, the standard error is the standard deviation divided by the square root of n. More on that in the near future. Sample variance, which we're going to visit here in a second, is the average of x minus x bar squared, also equal to the standard deviation squared. That's where that comes from. Kurtosis, skewness, the range, which is the difference between the minimum and the maximum, easily enough, and the sum, which is just add them all up. So, of course, if I add them up and then divide by how many there were, that's the regular formula for the sample average, which is the first of our moments that we would want to talk about. So over here in the scribble, I've got regular old mean of the data, which is just x bar. You know it and love it. It's add up all the data and divide by how many there were. So, okay, I think we can handle that. Let me get rid of those red boxes because we don't need them. Let's see if it does check out the way I think it will. I'm going to take this sum. I'm going to divide the sum by the count, and I should get that number. And doing the quick eyeball math, it looks like it's going to come out correctly. So I'm just going to verify. Equals. Add up all of the x's, the sum of all the xi's, divided by how many there were, should be 0.424851. Yep, perfect. That's exactly what that is. So all of these should make some degree of sense already at this stage in the class. Now these are our univariate statistics. We haven't talked about relationships between multiple variables yet, but we will get there very soon. All right, a pivot away from Tesla stock. Let's go back to transformers, more than meets the eye. So this class, this data set that I use in my 291 class is kind of fun because they laugh that it's about transformers and they say, oh look, I've got this survey of people, I ask them all how tall they are and I get some data and I notice that one of these people happens to be Optimus Prime, who is a giant robot from space. This is from the Transformers movies and comic books and other things, so it's a good laugh. But we can use this simple 8 observations data set and some calculations to build simple things like mean, median, mode, variance, standard deviation. These are things I'm going to want, right? These are the moments that I'm going to want. And some other things from scratch. DA662 is an accelerated class. We don't get to do all of those. So right off the bat, I'm going to tell you the weighted average, the geometric mean, the mid-range, which is actually just the point that's equidistant between the minimum and the maximum, we don't need, although the mid-range is simple, so I may come back and give it to you. The interquartile range, the 25th and 75th percentile, we may not need to calculate right now in this class. The coefficient of variation I'm not going to bother with. That's really only one number, but I'll put 2 slashes over there. The standard deviation I'm definitely going to want. The minimum, the maximum, the range, I might as well. The mean, the median, again, I might as well. The mode, a quick cursory look at these numbers will reveal to you 64, 65, 66, 68, 70, 71, 73, 236. Unfortunately, none of these 8 people who were surveyed are the same height. None of these numbers occur any more often than any of the others. So the mode is either none of them or all of them, depending on your preference, and both of those are unsatisfying answers. Then the variance the standard deviation, and things like z-scores might be a good idea to get into. Now, the skewness of this data, the formula for skewness is slightly cumbersome, so I'm not going to bother calculating it from scratch, although Excel will do it for you. And the proportion of values within a certain statistical distance from the mean. Now that's an interesting question too, because, and the mode of the z-scores is going to be like the mode of the data, because we just looked at something called Chebyshev that said that a certain proportion, Chebyshev's inequality says that a certain proportion of the data must be within a certain statistical distance from the sample average. Well, okay, we're going to see if this data set is a little bit counterintuitive in some way. And be prepared, it may surprise you. So let's start with some of the simple things. So if I want to go ahead and fill in some of these boxes, the mean of the data, for instance. Well, right off the bat, you are going to notice that Optimus Prime is a giant robot from outer space, and being 236 inches tall, which is almost 20 feet tall, 19 and, goodness, he's a tall fellow. Optimus Prime is going to move the average in this data set quite a lot. So the median, we sort of extol its virtues as being a bit less susceptible to outliers in comparison to the sample average. Let's go ahead and make that comparison. Suppose you don't know that Optimus Prime is a giant robot from outer space, and you haven't made any sort of dogmatic decision about whether you want to remove him from the data set as an outlier. You just go ahead with all 8 of these observations, thinking nothing of it. Well, all right, equals average. Yes, sure enough, there's a formula for the average of these 8 observations. 89.125. If you wanted to, you could say equals sum. There's a formula, there's in Excel for the sum of a set of numbers. You say something like the sum of all of these, and I can see very easily that there are 8 of them, so I'll go ahead and divide by 8, and hopefully I get the same number twice. Yes, of course, it's just the regular formula for the sample average, which we all know and love. So I'll take that, I'll copy and I'll paste it up here. Mean, I'll say just give me the value, keep the green, that looks nice. Okay, I figured out the mean. Now let's figure out the median. And I go through and I say, someone is very kind to us. They've already been ordered smallest to largest. And if I wasn't sure, because I had a larger data set, like this one, going back to the Tesla stock from a moment ago, I have a larger data set here, so I might want to think about sorting the data, which I can do, right? There's a sort button up here, but I can see from this data set that they are already in order, smallest to largest. So thank you to whoever did that. I'll go ahead and say here are the first 4, here are the second 4, and I know that when there's an even number of observations, the convention is I'll treat the median as whatever is halfway in between these 2 observations. Halfway in between 68 and 70, fortunately for me, they're both integers, so I know that that's going to be 69. I'll pop up here and say the median is 69. Well, 89 as a sample average is indeed very, very tall. You would look and you would see that 7 of my 8 individuals are shorter than that, in fact, by quite a lot. They're all at least a foot shorter than average. And then there's the other fellow, Optimus Prime, who is something like more than 10 feet taller than average. So I'll go ahead and ask the question, what would have happened if I had noticed that this was an outlier and dropped it, which I can do using the delete button, or which I can do by simply selecting a different subset of the data. So be careful throwing data away in a way where you can't recover it. Control-Z is not always available. Let's ask the question, what is the average? What is the average of just these 7 observations if I had known that Optimus Prime was an outlier and made the executive decision not to include that one datum? In case anybody didn't know, the word data is actually plural, so a singular observation is a datum. But it's 68.1428571 1, 4, 3, depending on how you want to round. Okay, well, that's quite a lot closer to the median, 69, than the average, including this outlier, is. You'll also notice that if I calculate the median, excluding the outlier, I still get 68. So including Optimus Prime takes the median from 68 to 69. Not a huge deal, but including Optimus Prime takes the average from 68 to 89, which, even though this data is artificial, is perfectly representative of that usual kind of story about the median being less susceptible to large changes in the data set or inclusion of really erroneous data. We're fortunate here, this erroneous data is not a typo. It's not data from a different spreadsheet that wasn't supposed to be here in the first place. It's not something that an intern might have made a mistake with. For instance, if you didn't know you were supposed to use the closing price for Tesla stock, and you used the opening price, would that have affected your results? Yes, of course, in some unknown way. The high price and the low price also look more or less the same, and they do capture much of the same information, but any of these 4 measures of the stock price on that day would have given you different results regardless of what your question about the data might have been. So this sort of thing is always fraught with at least a little bit of peril that somebody will make a Scribner's error. But here we're not dealing with that, we're just dealing with a giant robot from outer space. He really is that tall, and if you know anything about the Transformers canon, you'd know that Transformers canon is actually quite a mess, and in different versions of Transformers, Optimus Prime is much, much taller or much, much shorter. In the 291 class, this is a great running gag. Everybody has a laugh, and it's fun for me too. I don't know how tall Optimus Prime really is. He's a fictional character, but he clearly does not jive with the heights of these fairly typical individuals in the other 7 observations. So whether he's an observation that you want to include or not is just the sort of example you're going to encounter in a real business setting. Make your own decision. Okay, so moving away from measures of central tendency. We've got the mean, we've got the median, we've got this nice sort of duality between the mean and the median where maybe there are some preferences for what you want to use here. Let's talk about measures of spread, things that tell us how much this data is spread out. I can do certain things as far as plotting a histogram. I've only got 8 observations. Here's an incredibly unhelpful histogram. Thank you, Microsoft Excel. Thank you for presenting that beautiful, beautiful picture. Well, let's try adding some bins instead of 2, which is rudimentary at best. Let's say 5 bins. You'll see it doesn't really get any better because all of the observations are over here except the one giant robot from outer space. So let's bump that up to not 51. Although the number 51 is relevant when you're talking about robots from outer space. Let's bump that up to 10 bins and see that, yep, sure enough, it's really not doing much good. So goodbye histogram. For now, you're not going to help. Let's talk about classical statistics that tell us things about the spread in a data set. Well, the minimum of the data set is easy enough. I can see that the small number is 64. The maximum of the data set is easy enough. I can see that the giant number is 236. The range being, of course, equal to the maximum minus the minimum, this number minus that number, is 172. So the difference between the shortest person in the sample and the largest person in the sample is 172 inches, which is something like 15 feet. That's an enormous number. And if you want the mid-range, the point that is exactly in between 64 and 236, the formula for that is a plus b over 2. So I'll go ahead and tell you the mid-range, the point where you would be exactly the height in between the shortest and tallest person, is equal to, we might as well, 64 plus 236, close those parentheses, divide by 2, 150. All right, so somebody who's exactly 150 inches tall is as much shorter as Optimus Prime as they are taller than Michelle in this data set. Great. I'm not going to bother with the percentiles or the interquartile range in this case. We have a very small data set, so the percentiles are going to be calculated by linear interpolation, which is a bit lossy to begin with. It's not super helpful. But we want to talk about the variance and the standard deviation. These are the second moment and its sort of normalized regular units counterpart that go along with the mean, which is our first moment. So flipping back to here, everybody remembers that the mean of the data set is just x bar, this thing that we learned in, say, third grade or somewhere along the line. It's equal to adding up all of the data and dividing by how much there was. The variance of the data is a similar process. It is, in fact, an average. It's not the average of all of the observations, xi. And if anyone's wondering what xi is in this case, sum of all the xis are the 64, 65, 66, 68, 70, 71, 73, 236. It's the sum of all of those, exactly as we did when we calculated the average down here. So the variance of the x's, which I'll write that way using x's, apostrophe s, is equal to the sum of all the, watch, it's still the average, but it's the average of a function. I'll say xi, one of my observations, minus x bar. Some people are taller than average, some people are shorter than average, and xi minus x bar tells me how much taller or shorter than average they are. Xi is how tall you are, and x bar is how tall the average person is. But some of those are positive, some of them are negative. They actually average out to 0, so I'm going to square those and make them all positive. And then I'll divide by, there's a problem. I'd like to divide by n, which is the number of observations. And indeed, as you saw in the slides and in the other video, that is the formula for the population variance. The quirk here, as I mentioned, was xi in a small sample. If you have a lot of small xi's, those are going to move x bar and make x bar small as well. So xi and x bar tend to be a little bit too close to each other because x bar looks like the xi's. Well, what does that mean? If they're a little bit too close to each other, then this entire term up here tends to be a little bit too small. And if it's a little bit too small, you might want to rescale the denominator to compensate. And that's what we're going to do. I'm not going to divide by n. I'm going to divide by n minus 1. I'm going to have a degrees of freedom correction in the denominator to account for the fact that the numerator here is a little bit too small. In a very, very large sample, x bar is going to be very precise. It's going to be close to the true population average, mu, if we want to call it with the Greek letters. So this n minus 1 isn't going to have a lot of influence. It turns out that this is the correct way to do that, that adjustment to make this an unbiased estimator of the variance. So I'm going to put a hat on variance over here so that this one has a hat as x bar does. So x bar is your sample variance in the same way that variance, which I've just put a hat on, is my sample variance. But we've got a letter that we use for that as well, just like x bar. We call this s squared. Okay, so s squared is the estimated variance, and it's got this n minus 1 in the denominator. Notice that Excel is going to have two different versions of doing this. If you want to use Excel to just spit out the number, I come down here and say is equal to var. Can it do it? Yes, it can. There's one var.p and there's one var.s. I'm going to verify manually that var.p is the one that uses population formula and divides by n, and then I'm going to verify manually that var.s is the one that uses the sample formula and divides by n minus 1, which is what we want. Okay. And when I say this is what we want, I mean that you're always going to work with a sample. You're going to want this. Although, it would be beautiful if when we move to measures of relations between two variables, it would be really wonderful, goodbye, if I could have a scenario, I closed one of my windows here, it would be wonderful if I could have a scenario where, there we go, It would be wonderful if I could have a scenario where it doesn't matter whether you divide by n minus 1 or regular old n, and in fact, we are going to have that property when we get into correlation and the slope of a regression line. They are going to be immune to this whole topic, which is nice. So keep track of that n minus 1, very important right now while we're talking about statistics in relation to one variable only. Okay, all right. Now, how do I put this together? Pop back to here. And I could use var p, I could use var s. You know what, I'm going to do it from scratch first. I think I know the formula. I think I just saw it. It gave me a column here that says use this column for calculations, and I can follow instructions. So I'm going to buy myself a little bit more space, and I'm going to say I want xi minus x bar, right? I'm supposed to take the average of all the xi minus x bar and then square those. So I'll go ahead and come over here and say, actually, maybe I'm going to need one more column. So let me have xi minus x bar. And then in the next column, I'm going to build xi minus x bar squared, which is easy enough. Now this one will be equal to, what is xi? 64. What is x bar? Okay, well, x bar is over here, 89.125. I'm going to do the thing where I start typing these in and then I double click and send this all the way down to the bottom. So I'm going to go ahead and mark this E4 to tell Excel don't move that when I do the double click. Okay, B3 minus E4, which will never move. And sure enough, 64 minus 89.125 should be something like negative 25.125. I'm going to double click on this, and then I'm going to verify that it worked properly. Now it wanted to go all the way down, which is fine, but not necessary. What did it give me here? It gave me B4 minus E4. Yep, that's correct. That's xi, that's x bar. Here again, B5 minus E4. And in the 291 class with the undergrads, although most of you in the 662 are going to look at the dollar signs and say, yeah, no sweat, we know how to do that. In the 291 class, that always blows somebody's mind who has never seen it before. So, fair enough. I've got xi minus x bar for each of these, and I'm going to go ahead and calculate equals xi minus x bar squared. Here's my xi minus x bar, and I know how to square it. Just raise it to the power of 2. There's a 631. That's not a small number, and let's drag that down. These numbers get as large as 21,000. So I can tell right away that the variance is going to be a very large number. I'm going to add up all of these, and then I'm going to divide by n minus 1, which in this case is 7. But hang on. This is equal to sum of, let me grab all of the xi minus x bars, x bar squared, sorry, xi minus x bar, close parentheses, squared, and divide it by 8, which is the wrong number. Let me do that again. Say equals sum of all these observations divided by 7. Okay, all right. So the larger one is indeed a bit larger. This one would be the formula for the population variance, which just had n in the denominator. And the other one would be the formula for the sample variance, which has n minus 1 in the denominator. And I sure hope, all right, these are from scratch. From scratch. I sure hope Excel does it and gives me the same number. So Excel has a formula here, var p, var.p, and then I'll just feed it the original data and see what happens. It's a miracle. That's the same number. Okay. I'd like to stop doing that. And let's go ahead and get the other one. So this one is going to be equal to var.s, which is the sample variance instead of the population. Again, this is the one you want to use. If you're not sure which one to use this one. There we go. And if it shows up on a homework assignment or an exam and you're not sure which one to use this one. Let me go ahead and grab all that data. Close the parentheses. Magnificent. It's the same numbers just like I expected. So these that I built from scratch are indeed the same as these that Excel will give me using varp or var.s, which is what we actually want to use here. Now this number from var.s, 3531.55, is the variance. And I'm going to paste it right there. We have what we wanted. Now, variance sigma squared. Sigma is what we would normally call the population variance. So I'm going to go ahead and say this is actually S squared that we're working with here. And the standard deviation that I'm going to talk about right now is not sigma, the population version. It's going to be S, the sample estimate of the population variance. Okay, what is standard deviation? Well, standard deviation, which we call SD, or SD of x's, is equal to, easily enough, it's the square root of the variance of x. So let's just say the square root of s squared. And the square root of s squared sounds like a tautology because it's just going to take us in a circle right back to s. Notice also the way that this notation is built to remind you what everything is. That number we just saw, 3,000, is a lot bigger than the numbers that go with the height of the people in this data set. So how can it be that the spread of these numbers is measured in the thousands when the largest number, which is even ridiculously large because it's Optimus Prime, is 236? Well, it's in the thousands because the units on these are squared. That's why we don't like variance, and that's why we remark that variance is s squared. Standard deviation is the original s. I had to square them to make them all positive when I did this, take the average game. That's fine, but I don't really care how many square inches tall these people are because square inches don't make sense as a unit of height. I'm going to bring it back to regular old inches, s, and this is going to give me a number that says something about how far away from the average height most of these people are. So I should see a number for s that is something like, well, 64 to 70. And the average height is 89. If I see a number like 10, 20, 30, 40, or 50, it's a number that makes sense because 89 is the average, and these numbers are, say, 30, less than that, and then, of course, Optimus Prime is very, very tall. So I'm looking for maybe a double-digit number for the standard deviation. Of course, standard deviation is just the square root of the variance. So let's do it. It's equal to SQRT, parentheses, here's my sample variance, close the parentheses, and the moment of truth when I hit the equal button, 59.4269. Sure enough, my standard deviation is in the double digits, saying a typical person in this sample is about 59 inches taller or shorter than the other typical person. That kind of makes sense. Optimus Prime is doing a lot of work here because, of course, he is 150 inches taller than this hypothetical average person. He's quite enormous. Okay, that's variance and that's standard deviation. Where does standard deviation live in the big picture, the other sorts of things that we've been talking about? Well, when we have the normal distribution like this one, sigma down here on this horizontal axis, again, talking about the population here in a true normal distribution, so it's sigma instead of s, but that's it. That's the standard deviation. In a normal distribution, which we're going to invoke when we talk about confidence intervals and asymptotic testing, whatever the average is, something like 68% of observations will be one standard deviation above or below, within that range. No more than one standard deviation above or below average. Okay, and well, you can see over here that actually all of the humans in my sample are within one standard deviation, which is 59 inches of the average height. 89 minus 59. If you were something like 30 inches tall, or shorter than that, you would be more than one standard deviation below average. But nobody is that far out except Optimus Prime, so that makes sense. And then 95% of data should be within, it's 95.4% of data should be within about 2 standard deviations of the mean. If I want exactly 95%, it's going to be 1.96 standard deviations. And for a normal distribution, 99.7% of observations are going to be within 3 standard deviations of the mean. What I have down here, and we're not going to do coefficient of variation, so here's some friendly advice. Preserve units and never give up. Okay, preserving units means that talking about the inches of height for these people, I should really compare their height to other heights in terms of things like standard deviation, not in terms of variance, which has square units, hence the exponent. All right, so standard deviation is going to do some good work for me. The z-scores down here, and skewness, which I'm going to skip, are something that you might remember. So I'm going to go ahead and eliminate these 2 columns. I hope nobody needs them. And I'll pop back to the whiteboard to remind myself what a z-score looks like. So a z-score is a recoded flavor of the data, like translating from one language to another. Zi, notice that it has an I subscript because there's one of them for every observation. Just like this xi minus x bar, there was an I subscript, so there's a different xi minus x bar for every observation. But Zi is xi minus x bar, just like we had a moment ago up here, but not that, divided by the standard deviation. What is this going to do for me? Well, it'll say this person is a certain amount taller or shorter than average, but if I divide that by the standard deviation, I get not how many inches taller or shorter than average they are, but how many standard deviations taller or shorter than average they are. Okay, that's pretty handy because it tells me exactly where in the distribution they live. The distribution isn't going to look like this. We saw the histogram for these 8 people and their height earlier, but this is a nice construct as far as how far off of this could it be. And we also have Chebyshev's theorem, which is going to tell us something about what proportion of the data could be more than a certain number of standard deviations out there. So we do have, even though this seems like perhaps a little bit too simple of a model, we do have some hard rules for how wrong this model can be, and it turns out it does pretty well. So I'm going to calculate these z-scores for each observation and basically translate the data into, notice, xi has units of inches, x bar has units of inches, and the standard deviation has units of inches. So zi is going to be unitless just in terms of standard deviations. Remember, standard deviations are a measure relative to the original data. So zi is going to be truly unitless and nice to look at. Let's do it. Back to the data, and I will make zi. Zi is equal to, now I just erased the xi minus x bar, and I could have recycled that, but we'll do it from scratch. So I have, I need some parentheses. I'll say xi minus x bar, and again, this x bar is going to be something that I want to not change when I change what row or what column I'm looking at. So I'll go ahead and throw in the dollar signs, and if you're saying, hey, you could actually do that with just one dollar sign, you don't have to do it with 2. Okay, well, old habits. So I'll throw that in there, and then I'll say divide that by 59.4269, and you could just type in the number, but once again, I'll make sure that every time I highlight this, I have these nice color-coded boxes over here. If you appreciate the fine things in life the way that I do, you'll appreciate that someone at Microsoft, which I don't normally say nice things about Microsoft, but someone at Microsoft many, many years ago had the bright idea to color code these boxes when you throw them into an Excel formula, and that is actually very pleasing. So 64, let's do the quick eyeball check. 64 looks like it's let's say 25 less than the average, and the standard deviation is about 60. So this is a little bit less than 1/2 of a standard deviation below average. Sure enough, 0.42 standard deviations negative, meaning below average. And taking that all the way down, I see that everyone is below average and less than a standard deviation, except Optimus Prime, who is, of course, almost 2.5 standard deviations taller than average. That makes sense. And this is broken now, so I'll go ahead and get that out of there. Now, what can I do with the z-scores? Well, I could talk about the minimum z-score or the maximum z-score and say, oh, well, you know, there's only a variation of something like 3 standard deviations in this entire data set. It's not really super helpful. You can have data that varies very little, or you could have data that varies a lot, and in a large sample you might have just a tiny number of observations that are way, way, way out there in the tails. Now, looking at this, 99.7% of observations are between -3 standard deviations and +3 standard deviations above or below the mean. But the normal distribution actually has support all the way down to -infinity and all the way up to +infinity. So any number could happen. They just are incredibly rare in a normal distribution. Over here, you can ask the same question about the height of people, which, by the way, the real population height does, in some samples, look like a normal distribution, as do many other variables relating to people. But Optimus Prime is an oddball here, and he seems to be quite far out in the right tail. So z-scores, we could talk about the distribution of those. Mean, median, mode of the z-score, just like the regular data. And that's an interesting point, because the z-scores are, in fact, still the same distribution. All we've effectively done is relabeled the horizontal axis so that it looks like this, so that whoever is perfectly average has a number corresponding to 0. And look at the formula. If you are, in fact, exactly average, xi is equal to x bar, then the numerator here will collapse, xi is equal to x bar, so xi minus x bar is 0. And your z-score will be 0 if you are perfectly average, putting you right smack in the middle. And that's all the z-score does, is rescale the horizontal axis to make your distribution look like this. If I show you, for this data, the histogram, it will be just as uninteresting as it was the first time around. These numbers down here on the horizontal axis have changed because we're looking at z-scores instead of the original data. But if I pop over here and say, give me 10 bins, it's the same picture, right? Just like the meme. Corporate needs you to find a difference between these pictures. It's the same picture. So, okay, get that out of here. Z-scores. Then, remembering, perhaps I don't care about the minimum z-score, which is this number. So I'll at least bring it over here and say that's what it is. It's not interesting, but that's what it is. What's the mode? None or all of them. It's the same story. How many of these observations are within 2 standard deviations? Okay, now we're talking about something interesting. So being within 2 standard deviation, I seem to recall Chebyshev's theorem said that no more than 1 over k squared of the data could be k standard deviations out. So 2 standard deviations out, you couldn't have more than 1/4 of the data out there. Well, let's count and see how many observations are actually beyond 2 standard deviations. This is half a standard deviation below average, less than half, less than half. Nobody is except Optimus Prime, 1 out of 8. So 87.5%. Because I say how many are within. 87.5% of observations are within 2 standard deviations. Fair enough. Chebyshev says that it's got to be at least 75%. In this case, it's 87.5%. And if I go to how much of the data is within 3 standard deviations of the mean, Chebyshev's theorem says that no more than 1/9 of the observations could be farther than that far out. So something like 91%. Okay, and let's go back and see how many are within 3 standard deviations of the average. And sure enough, it's all of them. Everyone in the sample is within 3 standard deviations. What number did I just say for 1/9? Would have been 1/9 would be 11%. I'm not sure what number I just said, but I don't think it was that. Right? So it'd be 88.888 would be the amount that should be here. But I see in fact 100% of observations are within 3 sigma. It's impossible for any distribution to have less than 88.88% of the data within 3 sigma, according to Chebyshev's theorem. And that may not sound useful, or it may sound a little too convoluted or too abstract because we're talking about Chebyshev's theorem. But Chebyshev in this case says that there is a hard limit on how many observations can be 3 standard deviations away. Well, what's 3 standard deviations? Who cares about 3 standard deviations? In the slides, we talked about outliers as being observations that are more than 3 standard deviations away from the mean. And I warned you that that was just a convention, but it is a popular convention. And I look at this data and I say, are there any outliers in this data set? So all of that was to answer the question, are there any outliers in this data set? And the answer is, according to that classical 3 standard deviations away rule of thumb, if you calculate the mean and the standard deviation using the full sample, nobody is that far out, even Optimus Prime. And the reason why Optimus Prime is not an outlier in this sample is because it is impossible by that definition for any more, according to Chebyshev's theorem, it is impossible for any more than 1 out of 9 observations to be 3 standard deviations away from the mean. Well, I don't have 9 observations. I only have 8. And if 1 out of 8 was that far away from the mean, that is in fact 1/8 is larger than 1/9 for those of you who are good with fractions. So according to Chebyshev's theorem, in this sample with 8 observations, it's impossible. No matter how tall I make Optimus Prime, I can add another 0 here, like that. It doesn't matter. He will never, this number will get larger and larger, but he will never be more than 3 standard deviations away, because the taller I make him, the larger the standard deviation is. Okay, there's a chicken and egg problem here. If you're wondering, why don't I just take the other 7 observations and use those to define the standard deviation and calculate the mean, which would then be a lot closer to the 68 or 69, which we think is the real middle of the data. In that case, you're already declaring Optimus Prime an outlier prior to calculating those, and sure enough, he would be more than 3 standard errors away after you had done that process. But you have started from the decision that he's an outlier. It's a bit of a silly example, especially because we're doing this Transformers thing, but all of that is to say you can never have a rule that perfectly captures what is or is not an outlier, regardless of sample size, regardless of this, regardless of that. You're going to have a convention like 3 standard deviations away, but it will never be perfect. It's always just going to be a rule of thumb that some amount of personal insight is going to have to be necessary in order to keep it in check. I would go over here and say, are there outliers? According to our 3 standard deviation rule of thumb, no? Question mark? It doesn't seem that there are any outliers here, but make your own decision about whether the giant robot from outer space really belongs with the rest of the data. Perhaps he does not. Okay, one last piece here before we start pivoting to talking about the relationships between multiple variables and that bridge to regression models, which are Module 2. I'm going to come back to the whiteboard one more time, and I'm just going to do one example of a confidence interval. So I've got a sample here for how tall people are, and I've got a sample over here for, say, Tesla stock and the daily return or the intraday range, whatever it might be. And I do have the tools to make some sort of a statement about the population here. And the population statement that I want to make is, how tall is the average person? Well, I don't have the average person in my sample. In fact, there is no average person, right? No, we're all very, very high dimensional entities. Nobody is average. Some people are close to average in some ways, but there is no average person. So how tall is the hypothetical average person who doesn't really exist, who lives in the population, or is an abstract concept based on the population, which I don't have because I only have 8 observations? Well, I'll make a confidence interval. I know, based on the regular sort of theory, that the average of my sample is going to be distributed according to something like a normal distribution, which is what the central limit theorem tells us about the average. And I know that the average of my sample should be very close to the population average. Okay, how close? Well, if the population average is some number, then 95% of the time it's going to be, my sample average is going to be greater than, say, 1.96 standard errors below the population average. And I know that my sample average is going to be 95% of the time less than, say, 1.96 standard errors above the population average. So I can come up with a range taking this population average and saying that the distance between the population average and my sample average can be no more than 1.96 standard errors 95% of the time. Well, that's the same as saying that the distance between my sample average and my population average can be no more than 1.96 standard errors 95% of the time. So my 95% confidence interval, last thing here, 95% confidence interval, which I'll just write CI, for the population average. And the confidence interval, we could say for mu, or we could say for x bar in relation to, I have x bar. So there's a function of x bar. This is just the sample average, right? My 89.125 that I have over there. I have x bar. There's a function of x bar that tells me the 95% confidence interval for the population counterpart to that estimate. I like that. What is it? Well, I'll take x bar and I'll remind myself that the true population average, 95% of the time, is going to be within 1.96 standard errors. So it can't be more than, say, x plus 1.96 standard errors. Let's fix that 9. Hey, fix the 9. Fix. Or less than, say, x minus 1.96 standard errors. So I'm going to say x plus or minus 1.96 SE. And then I'll come back with the color coding to remind you the important pieces. X bar and the standard error. Now, what is this? Go back to Excel for the number. And what is this? That's actually S, the standard deviation, divided by square root of n. All right, so again, Excel. It's there. It's there, I promise. The piece in the middle, if you're wondering where that thing came from, okay, well, I'll tell you. This one, normal distribution. And it also relies on the 95% decision that I made. I want to be right 95% of the time, and I know that the distance between x bar and the true population average 95% of the time should be no more than 1.96 standard errors. If I want to be 99% sure, I'm going to need to go out to, say, 2 point something standard errors, Or if I don't want to be 95, if I just want to be 90% sure, I can make a narrower confidence interval. But this 95% and the 1.96 are the numbers that everybody starts to recognize. If I know x bar and I know the standard error, there is about a 95% chance that the true population average, the true average height of everybody, not just these 8 people, but everybody in the population, is in that range.